Good morning. Welcome to the second lecture of Introduction to Model Checking. Okay, good. Then let's start. I explained you in the first lecture that in model checking, the first thing that we have to do is we have to talk about models, because that's what we're all going to check, models. So the model that we're going to use is what they call transition systems. So what's a transition system? A transition system is a kind of a directed graph. And this graph is basically extended with a couple of notations. So roughly speaking, the idea is that we have a real system and we're going to make a model. And this model is basically this semantic model. And this model, the idea is that we're going to represent a couple of essential features of the system. The first is the state. So think about a traffic light. The state of the traffic light is its current color. The stepwise behavior, which means how the system will evolve. The traffic light could switch from, from red to orange. That could be a change, that is a transition. Then we have to start somewhere. Maybe initially the traffic light is red. And there is additional information about communication or even execution of actions. We call this, or execution of statements. This is what we are going to call actions. And that will become very important in the next lecture because we're going to use those actions to actually take models of small components and try to glue those components together to get a model of a larger system. What will be important is that we also have properties about states. A very simple property would be if the traffic light is green, the property is the traffic light is green, which is obvious. The other property is not red, which is also obvious, but maybe there are other properties that we would like to state. And what we do is we associate this information to the states of a transition system. So formally, we're going to talk about 6 tuples. We have 6 ingredients, and this is a transition system. So a transition system consists of a couple of states. This states is a countably infinite or finite set of states. So this is the first difference with finite state automata. Finite state automata have finitely many states. In a transition system, there can also be infinitely many states, but they are countable. So we can number them. Yeah? Then we have a set of actions. And those actions we are going to basically use on the transitions to glue transition systems together to build larger transition systems. As I said, this is going to be important in the next lecture next week. Then we have a transition relation, which is a ternary relation. So it contains triples. And the triples are of the form we have a source state, we have a target state, and we have an action that tells you basically if the current state is in this set and we take a certain action, then the next state will be a state over here. So the typical kind of relation is the following. We are currently in state small s, so this small s is a member of capital S. And then the relation says, okay, S alpha S prime. So actually this is already a shorthand because now you may say, where are the triples? Well, the triples are as follows. You have S alpha S prime, which is a member of this transition relation. Yeah. And this means that we currently are in state S, then we can take action alpha, and the next state then will be S prime. I'm going to use this abbreviation which is on the slide. So the abbreviation that we're going to use is S alpha S prime. So this is just a shorthand, this thing, for what we have written here formally. Good. Then we have a set of initial states. Can be typically one state, but can also be more. If there are more than one state initially, that means that the system non-deterministically can decide where to start. Okay. Then we have these elementary properties. So I would like to associate certain information to the states, and these are given by atomic propositions. The traffic light is green, the traffic light is not red. So these are members of this set AP. And then we're going to associate to every state the elementary properties that hold in that state. That can be several, and typically it's a set. So what we have is we have a mapping, a labeling L, that maps every state to a set of the atomic propositions. Good. We will see several examples during the lecture of these kind of transition systems. So here is a very simple transition system for a beverage machine. It has 4 states: P, Select, Coke, and Sprite, with the transition relation indicated by the arrows. So there is a transition from P to Select. And for simplicity, I omitted these actions alpha. They don't play any role for this example, so let's not bother about them too much. So this is the state space. We have some initial state. The initial state is P because it has an incoming arrow basically coming from out of the blue, so to speak. So that's the initial state P. Then we have, maybe we have actions, so now we have enriched this with actions. So this could be the action coin. This could be the action get Coke. This is the action get Sprite, if we move from Sprite to P. And in Select, apparently there is an action TOR here and an action TOR there. So the first thing you see already that this also can, like automata, be non-deterministic. In this state, there are 2 TOR label transitions, namely one going to the left and one going to the right. Yeah, both labeled the same. The set of atomic propositions, I indicate them here with colors. So this is the, let's say, the elementary properties. Suppose that the elementary properties are something of the form pay and drink, red and green. Then we have to define which states satisfy which properties. We say, well, in the select state, no property holds. In terms of a color, this means that color is simply transparent, it's white. Then the labeling of the state P is labeled with the singleton set P, indicated by the red color over here. And the labeling of the 2 states on the bottom, Coke and Sprite, are labeled with the singleton set drink, and that means I colored them green. Good. So there are 2 main differences with respect, well, 3 main differences maybe with respect to finite state automata. First, the number of states can in principle be infinite. This example is finite, but we can also, later we will see infinite state transition systems. There is not something like an accepting state. So it's not the case that a label transition system accepts a word and based on this word moves from one state to another state. No, it models the behavior of a system. Yeah? So it exhibits certain actions like get Coke, coin, or get Sprite. Now you may change the labeling, so now I keep the same label transition system, but I change the labeling. So let's suppose now I simply say every state, the set of atomic propositions is identical to the set of states, and then the obvious labeling would be the labeling every state is labeled with itself, and that means formally L of S is the singleton set containing S. So you see the coloring scheme of the pictures changes, but of course the rest of the picture stays the same. Yeah. Good. So what is the behavior of such a transition system? And I try to write this down here as a kind of pseudocode algorithm. So, yeah.
Could you go back?
Yes.
Shouldn't the transitions going up from select be different? Because then we can really decide if we want Coke or Sprite.
What is the question? You have
the transitions going out from the select state.
Yes.
Shouldn't they be different so that we can know?
No. So the transitions are still the same. Yeah. So still you have a transition that moves from Coke to Sprite. So simply what you have is you have of select, you have a TOR transition, right? That's the label, and that it moves to Coke. That's one transition, and we have a transition that says select TOR to Sprite. These 2 transitions were there in my first transition system, this one, where we had this labeling. The only thing I changed is the labeling. It doesn't affect the transitions. The transitions are still the same. The only point is that now the labeling of these 2 states is different. But the automata or the transition system is still non-deterministic. Being in the state select, you can do a TOR transition. you either end up in the coke state or you end up in the Sprite state. This remains the same, no matter what is the labeling of the states. Yeah? Good. So to make this more clear, I hope this is a kind of pseudocode that tells you what is the possible behaviors of a transition system. So first we have to fix where do we start. Now typically we have one initial state and it's clear you start in that initial state. Now suppose there are two, then where do we start? Well, you select this non-deterministically. And the idea is that an initial state simply tells you what is the possible initial state where the system can start. Yeah? It has no preference for one over the other initial state. It doesn't flip a coin and says this happens with 50% and that happens. No, it's simply completely non-deterministic where you start. Good, then the question is how to continue. Well, pick such an initial state. Suppose that we pick initial state S from the set of initial states. Then if S is non-terminal, what does that mean? If S has at least an outgoing transition. Yeah? Which means we need to have something of the form S moves with some action alpha somewhere. Yeah? If such a transition doesn't exist, S is terminal. We cannot continue. Yeah? So in the very simple case where this is a transition system, we start here and this is S, but it has no outgoing arrows, yeah, then we don't enter the while loop. So we have a non-terminal, then what do? We select non-deterministically a transition. So look at this S. This S has maybe several outgoing transitions. Alpha 1, alpha 2, alpha n. Which one are we going to take? Well, the transition system is describing the possible behaviors of a system, right? It's not an automaton waiting for alpha 1 as an input. No, it's something that describes what the system can do. Proactively, on its own. And that means you can either do alpha 1 or you can do alpha 2 or you can alpha n. So we're going to pick one. Yeah, so now we're going to select one. So what we're going to do, we're going to select one. Let's suppose we take this one. Yeah, so that's the one we pick. That means we go to some state. So this is some state S prime. And that means that's a transition we have selected. And then from then on, so we execute the action. The current state is going to be S prime, the target of the transition. And then we repeat the loop. And we do this until we reach a state that has no outgoing transitions. So one thing that you should have in mind, even if the transition system is finite, this algorithm pseudocode, will not necessarily terminate. Yeah? In case I can maybe go from S, I have a transition, let's say with alpha I can move here, with beta I can move there, and from S prime we can go back, maybe again with alpha. Then this algorithm will not terminate. Yeah, because we never reach a state that has no outgoing edges. Yeah, so the behaviors of transition systems are typically infinite, unless you have a state where you cannot continue. Good, that's also a major difference with finite state automata. Good, so what's now an execution? An execution is a possible, I would say, kind of output of this algorithm. Namely, how did you traverse the transition system? You maybe started with S0 because S0 is an initial state. Then we have selected perhaps initially alpha 1. We move to one of the target states, S1. In S1, we have again selected one of the possible output or one of the edges of S1, maybe alpha 2. We move to S2 and so forth. Now we call this executions. So executions are typically infinite. And then you can define what is the set of states that is reachable. Those are the states that you can reach from some initial state by actually running this algorithm. Yeah, so in my example over here, both states are reachable. Of course, initially this is already reachable because that's why we start. And this one will be reachable because as soon as we select here beta, this is S prime. Notice that a possible execution could be also something like this. We could start in S, we pick alpha. We start in S, we pick alpha, and we do alpha, and we always stay in S. This is always fine. This is also fine, right? There's also a possible execution. The reachability is basically a universal quantification over all possible executions. And there is another execution, namely that moves from S to S prime by doing beta. Good. So what are we typically doing? Question.
Is there a way that a state is not reachable?
Is there a?
Is there a transition system where a state is not reachable?
Yes, sure. I mean, I can write, I can add another state here. Yeah, maybe this, and this can maybe move here with alpha, but I will never reach S double prime. Yeah, it's part of my picture, it's part of my transition system, but I will never reach it because there is no possibility to start from, in this case, the initial state to go there. Yeah, even if I would, let's say, say that this is an initial state too, that will not change the matter. S double prime is still not reachable. Good. So what are we going to do in model checking? Typically we have a kind of system which is complicated. It maybe has several components. The double bar symbol stands for something like multi-threading. That will be dealt with in the next lecture. We map this system onto a transition system, so the structure we just have learned. And this is one of the inputs to a model checker. The other input is a specification that we get to this much later. So actually what we're currently considering is basically transition systems. So one of the essential inputs to basically every model checking algorithm. Good. Now, your model is typically not described by a transition system. Models typically are huge. So you don't want to specify, you don't want to draw a state space of, let's say, 10,000 states. Don't think about 1 million states. So typically you describe your system on an abstract level using some syntax, a language. And then what we are going to see is that these languages can then be mapped by means of a semantics, which means an interpretation of this language, of these terms, into a transition system. So the bottom line of the lecture of today is that transition systems are the elementary models, and basically almost everything you can think about, almost everything, you can model by means of transition systems. No. Good. So the first example that I'm going to show you, I'm going to make this explicit and by means of 2 examples. The first thing is hardware circuits. So I'm going to argue if this is a hardware circuit, then the semantics can be given in terms of a transition system. And because we are going to do model checking of transition systems, we can also do model checking of hardware circuits. The second example I'm giving are programs, sequential programs. So what we're going to see here, there is a sequential program, so there is only one component, P1, forget about the other ones, which is given as a program in pseudocode. I'm going to show you the underlying interpretation of such a program is again a transition system. Okay, good. So if we can do model checking of transition systems, we can do model checking of programs that give rise to finite transition systems. Okay, so the first example is a circuit, and I'll make it very simple. The circuit has a couple of input bits, so these are the inputs to the circuit. In my case, there are n Boolean inputs. So x1 is either 0, 1, x2 is either 0, 1, and so forth. Then we have a circuit. This circuit has a couple of registers, in my case k. They store, so they have a value, and these values are again Boolean, 0, 1s. And this circuit has output bits, in my case m output bits, y1 to ym, and again they are bits, so they're 0, 1s. I'm going to describe the behavior of this hardware circuit by means of 2 things. Suppose that I change the input. Then there are 2 things that I need to tell you about this hardware circuit. First, what kind of effect does this have on the registers? This is given by the function delta. Yeah? So for every register, I have to tell you if an input changes, what happens to this register. So for register 1, I have a function delta 1 that tells me if I provide the circuit with a new input, what is the new value of register 1? The same for register 2. I have k registers, so I have k functions. For every register, I have to tell you how is the register going to change. Good. Secondly, I have to tell you something about the output bits. So for every output bit, y1 up to ym, I have a function. So for y1, I have a function which I call lambda 1. That's going to tell you what will be the output bit y1 given what? Well, actually given an input plus the value of the registers. Yeah? Good. So what are these? The type of these functions are the following. So these deltas and these lambdas are all functions. We call them switching function, but that's not so important. What do they do? They take as input, first of all, the input bits. So the input bits are n tuples because I have n inputs. Every value is binary, so I have this set to the power n. Then those values also depend on the current value of the registers. How many registers do I have? I have k registers, so I have 0, 1 to the power k. Based on these inputs and the values of the registers, I'm going to determine the new value of the register or the output, either for register J or for output I. So the subscripts are going to tell you which register we're going to talk about, which outputs we are going to talk about. Good. So this is the ID. We have input values for all the bits. So A1 is the current value of x1, A2 is the value of x2, and so forth, and AN is the value of xn. We have also the current values of all the registers. So C1 is the current value of register 1, C2 is the current value of register 2, and so forth, and CK is the current value of register K. Now, what are these functions going to define? So we have those functions delta J. Delta J is given these inputs and these current values of the registers, going to compute the next value of register J. Only J. Similarly, we do for the outputs. We have a function lambda I that is actually giving the output value for the output variable yi. Good. And now what we're going to do is we're going to build a transition system for these circuits. And the first thing I'm doing, I'm trying to give you an intuition. We're trying to do this by means of an example, and then I will write you on the blackboard how this works. So what's the initial? We have to start somewhere. So the initial valuation is there are no inputs yet. So the initial valuation is for every register stores a certain value at the moment. Typically, these are only zeros, for instance. Yeah, you say basically by default, all registers initially are 0, which means register 1 initially has a value C01. The 0 stands for initial, 1 stands for the register we are talking about. So the kth register has an initial value C0 for that register K, which means C0K. For the moment, just assume all those C0s are 0. Now we're going to define a transition system. So the transition system, you should think about what's the state of this circuit. So what's the current state of the circuit is basically the value of the inputs plus the values of all the registers. Yeah, that's the ID. That will be the state. That will define what is the current state of this circuit. Then the transitions will represent the stepwise behavior. So they will be defined actually by those two functions delta and lambda, because they are going to tell us how the registers will change and how the output function will change if we change the input. Then the values of the input bits are actually going to change non-deterministically. Why is this? Well, we want to describe the hardware circuit. Somewhere from outside the system, someone is provided, maybe typically another component is providing the inputs. The system itself doesn't have any control on which input will come next, right? This is what the outside world is going to define. Somewhere here from the outside, someone is sending us those bits. We don't have control over which bits is going to be next? Will this be a 0? Will this be a 1? I don't know. So we're going to use non-determinism to model this. And then we have atomic propositions. I think in my example I will only concentrate on the y's. Now the choices that we're going to do is you could for instance say the current state tells you what's the current value of the input bits. You could decide to say, well, the current value of the output bits. In my example I will only use the output bits. And then there are registers that tell you something about what's the current value of a register. So basically here you're going to take the information which is already in the state, plus you can take also the output values. But let's look at an example. This is a very simple example. It has one input, one output, one register. One input, one output, one register. And what it does is the input is coming here. There is an exclusive OR here, there is an OR here, and there is an inverter over here. Good. So what's the output function? The output function tells you for y, so we have only one output function, namely lambda y. Yeah? What is lambda y? Well, it's the negation, so this is the inverter, of what? Well, of the output of this XOR, so this symbol stands for exclusive OR, and then here is an X, so that's the input to the exclusive OR, and the current value of the register. This brown over here is the current value of the register, that's R. Then what's the transition function? Then that tells us something about the register. So the register R is basically a disjunction, it's an OR of what? Well, of X, that's the blue incoming line, and brown, which is the incoming line coming from the register. So delta R is X or R. Yeah, so they are typically Boolean functions that tell you how to change the state. Good, so now we want to build a state space or transition system for this circuit. Now, what are the states? Well, there are the output function and the transition function. The transition system looks as follows. First of all, we have 4 states. Why is this? Well, we have one input, one register, they both are binary, so we have 2 to the power 2 many states. So that's hopefully clear. Then the first is, where do we start? Now, we can maybe agree on the fact that maybe the register is initially 0, so that will be true in this state and in that state. And now the question is, where can we start? Now remember that the output, the input to the hardware circuit is non-deterministic, right? The circuit itself has no control what will be the first input bit. What does that mean in terms of the transition system? It means that we will have 2 initial states. So these will be the 2 initial states. Yeah, because you don't know, the system doesn't know whether the first input bit will be a 0 or will be a 1. Yeah. Good, and this has been my assumption. If the assumption is different, then of course you could also start here and there, but then the assumption is that the register initially is 1. I make the assumption initially the register is 0. Good, and now we have to look at the transition function. So here is one transition. So let's suppose that we are in this state, and suppose that the input bit changes from 0 to 0. So it stays at 0. Okay? What does that mean in terms of my transition system? I stay in this state. Yeah. Good. Why is this? Well, I mean, actually, maybe I should write this down. So how is the transition relation formally defined? I can use the board over here. So the formal definition is the following. So delta Rj, in my case j equals 1 because I only have one register, but in a general setting I have more, is the following. It's a function that tells you take the current input values, take all the values of the registers. Yeah. This moves by some transition. Let's call this a Tor transition. That's my action. As the actions do not play any important role here, I just take an arbitrary symbol. And then we move to a new state, which will be A1 prime up to AN prime and C1 prime up to CK prime. Such that, so this is the input. This is the current register values. And then we define that Cj prime, in particular, what happens to those values? Cj prime is going to be delta Rj of A1 up to An, R1 up to C1 up to Ck. So what is important is that these values depend on these current state values. So this is going to be determined by this. So suppose that currently we are in the state x equals 0, r equals 0. This is A1. This is A0, A1. This value is C1. Now the system is going to change. Let's say the next input is a 0. So then this state moves to a new state. What will be the new state? Well, the new input. Let's suppose that x equals 0. So this now is the value A1 prime. Now the question is what happens to the register? And now it becomes important. This value of the register depends on those two values, not on the new input. So that means that in this case, we will have that r equals, well, the OR of this value, so 0 or 0. And that is 0. So that explains the self loop here in this state. What happens if the input becomes a 1? Then the input becomes a 1. So in that case, I move from the state x0, r equals 0, to the state x equals 1, because that's my new input. And now again, this register value depends on those two values, so again it's 0 or 0, which means 0. And that's the rightmost state over there. Good. So if we continue this kind of scheme, then we now concentrate on this state. X equals 1, r is 0. Now there are two possible successor states. Either the next input is a 0 or the next input is a 1. Good. If the next input is a 0, then what is the value of the register? The value of the register is the disjunction of those two values, and 1 or 0 is 1. Okay? If the input changes to 1, or actually stays at 1, then again, similarly, this value is the disjunction of 1 and 0, which is a 1. Good. I hope this is clear. If you continue this, you get this as a transition system. And the claim is that the behavior of this transition system models basically the behavior of this sequential circuit. Good. Now you can try to say, okay, what are the elementary properties? Maybe the elementary properties that we would like to say is basically that the output is true or the output is not true. So we want to indicate whether this output is high or low, true or false. And in this state, for instance, 0 and 0, then we have to say it's not the case of this exclusive OR, and that's true here, so that's why y is true in that state. Formally, what we say is that the labeling of this state is a singleton set only containing y. Maybe if we also want to say something about x, then maybe the input here is 1, so therefore x holds. Maybe there r holds, and in that state, actually, in those two states, you can check yourself that y is false. So this output bit is low, because it's not that x and y are exclusive OR here. And in this state, you see now the example where we have a set, namely x is high, r is high, and actually y is high as well. So the labeling of that state is x, r, y. Good. How many states has a transition system if I have a circuit of this form? Suppose I have many gates. So in this example, I only have 3 gates, right? It's XOR, OR, and NOT. Typically, I can have many more. Here is even no input, so it's even very simple. We only have 1,000 gates, we have 100 registers, and we have an output. How many states do we get? We get 2 to the power 100 states. Yeah. Because we have to keep track of all the possible values of those registers, and there are 2 to the power 100 different possibilities. What about this? So the first slide says the number of gates is not decisive. It's the number of registers which is important. The second thing is, of course, that also the number of input bits is important. So this is a very simple example, no output, only an input, and again 100 registers. How many possible states does the transition system of this circuit has? 2 to the power 100, because these are all the possible different values of the registers, times 2 to the power 1. We have one input, and the input is either true or false, so we have 2 to the power 1. Yeah, so it's the number of registers and the number of inputs that is decisive on the size of the transition system. Good. That was my first example. So the bottom line of this part is basically every sequential hardware circuit I can model by means of a transition system. Actually, those transition systems in this case are always finite. They can be big, but they're always finite. One of the reasons why model checking was first applied initially only to hardware circuits, because there it was guaranteed that the models are finite state. Now for data-dependent systems, and think about programs, this is a bit different. So you can, for instance, not equally simply model in a transition system a situation like this. We are in a state, and now dependent on the value of some variable in the program, let's say x, we would like to go left or we would like to go right. So the current definition of the transition systems does not give us any means to model this. So this happens, for instance, in programs. So here you have just a loopy program. It says as long as x is positive, you subtract 1 from x and you add 1 to y. And the way I'm going to do that, because I don't want to introduce here, let's say, yet another programming language, what I'm going to do is I'm going to actually look at the control flow graph of a program. So what I did here is I take this program, and what I will do is I will use a graphical notation for programs. They look like this, they are graphs. They're not transition systems, right? They're graphs. They have locations, L1, L2, L3. Basically, they correspond to the lines in this program. Suppose that we start in L1, then what do we have to do? We first have to evaluate the guard x is larger than 0. Okay. If x violates the guard, that means we are not going to execute the loop. That means basically we go to the location which corresponds to those 3 dots. We should continue here, yeah? Which is indicated by this location L3. However, if the guard holds, which means if x is strictly positive, if x is positive, then we can take this, and I'm going to introduce this, this edge. I'm going to say if x is larger than 0, then what we're going to do, we're going to subtract 1 from x. So I'm already executing in this edge that I'm going to do the first assignment in the loop. Now what then I still have to do is the second assignment. So now I do the second assignment, I add 1 to y. Where do I end up? Well, I end up to the same program line over here, because then again I'm going to check whether I have to execute the loop or not, which is indicated here by going back to L1. Okay? So I hope it's clear that the graph on the right-hand side, which we are going to call a program graph, is a kind of faithful representation of the program on the left. Good, so this is what we just mentioned. The locations actually correspond to almost the line numbers, with one special thing, namely that I decided to take those 2 things together. So evaluating the guard and doing the first assignment is actually attached to an edge. So formally, an edge actually contains basically of a pair, namely a condition. The condition says x larger than 0 plus 1 or more actions. In my case, it's 1 action. The action says subtract 1 from x. In this case, there is only a condition, there is no action, and therefore there is no, let's say, statement or assignment going to take place. So therefore, I did not indicate this assignment. Here you could read this as the condition is true, which we typically omit for simplicity, and if the condition is true, we are going to increment y by 1. Good. So I'm going to argue and going to show you that every program graph, and mind, a program graph is for me a program. Every program graph can be described or gives rise to a transition system. So what's the state of such a transition system? Now, what do we need to know about a program to know what is the current state of a program? Well, first what we need to know is where is the current program counter, the location. Secondly, what we need to know is we need to know all the relevant data, which means all the values of all the program variables. In my example, I basically have 2 program variables, x and y. So in my case, a state of this system would be I am in some state in location L. The current value of x is 15, for instance. The current value of y is 10, for instance. And that is the whole information I need to model this as a state. Good. So let's look at an example of a run of this program. And for the sake of my example, I assume that x initially is 2 and y initially is 0. Then this would be a possible run. So every, let's say, picture of everything over here is a state. So that's the state of my transition system. So what's the initial state? Well, the initial state tells me I am about to execute line 1. So the program counter, the value currently is L1. Then we have agreed that initially the value of x equals 2 and the initial value of y equals 0. So these are the 2 values which I have over here. Good. Now I'm about to execute L1. So let's do L1. Remember, what are we going to do? We're going to check whether x is larger than 0. So we're going to check in this state whether x is larger than 0, which is the case because x equals 2. Which means we are able to execute L1. So let's do this. What then happens is that we decrement x by 1, so this 2 becomes a 1. Y is not touched. Now I am about to execute L2 because that's the current value of the program counter. What happens in L2? Well, x is not affected and y is incremented by 1. Where is the control flow of my program moving? Well, you just have executed L2. Then we go back to the beginning of the loop. So actually the program counter is changing from L2 to L1. Okay? Now, what you see is still x is larger than 0 because x equals 1. So we can subtract 1 and we move to L2. You increment y by 1, so you get y equals 2. You move to L1. Now we go, again, we are about to check the condition. And now you see that x equals 0. That means that we violate the guard of the loop, and that means that the next state will not be L2, but we immediately jump to L3, which is the ... Yeah, and think about the continuation of this loop, and there the program would continue. So this is indicated here. The program counter from this state moves to L3 because the guard of the loop is false. X doesn't change, y doesn't change. So we're currently in this state. Now this is one possible behavior of the program. Well, in this case, the only possible behavior if the input of the program initially is x equals 2 and y equals 0. We are going to allow programs to also be non-deterministic. That means that in general, a program may have several possible executions, because this is just an execution, right? This whole thing here, for the same input. Good. So now you can say, now the actions are basically in the transition system correspond to the assignments. So here I have 2 assignments, this x and assignment to y. Let's call them actions alpha and beta. I actually did the same in my program graph. This was my program graph before. I now call this assignment beta and this alpha. And that means that my transition system now looks as follows. And now what you see is now you can basically indicate in every step which assignment did you take, or which action did you take. And what I do here is I took the action loop exit, so here is the action loop exit. Yeah? So actually the program graph is a graph. There are conditions on edges as well as actions. And actions in terms of a program correspond typically to something like an assignment. Good. Now I would like to make this formal, and I would like to provide a mapping from any arbitrary program graph to a transition system. By the way, are there any questions so far? No. Good. So the first thing, I'm going to define what are type variables. So in my program I have variables, and I'm going to assume that every variable has a type, which means the value of this variable comes from a certain domain, namely this set, the domain of X. So Boolean variables, the domain of a Boolean variable is simply 0, 1. The domain of an integer variable y, in my case, is a natural number. The variable z, where these are colors, so this could be modeling the colors of my traffic light. Then we have to make sure we have seen the state of the program is the program counter plus the values of all the variables. How are we going to formalize this? We're going to formalize the values of all the variables by means of a function, and those functions we call evaluations. So what's an evaluation? Suppose I give you a set var of variables. Every variable is typed, so either it's an integer, a boolean, a color, whatever you want. And now we give a function, and I'm assuming up front this is type consistent. Type consistent means the value of a boolean is a boolean and not 27. The value of an integer is an integer and not a string, and so forth. And this function is going to map variables to values. So this is what I just have said. Type consistent means that if I take the variable x and I look at the value that eta is going to assign to x, this must be a value that corresponds as a member of the set dom of x. It must be in the domain of x. No type inconsistencies. That's what this actually says. What are the values? Now, we basically have different, all the variables, x, and we take the union over all the domains of all the variables. If I have a Boolean variable, if I have an integer, and I have a string, then this function is going to assign to this Boolean, to this integer, and to this string a value. So the codomain of eta is the union of the Booleans, the integers, and the string. Good. So I'm going to use this notation. Eval_var is the set of evaluations, the set of functions. Yeah, an evaluation is a function. It's a set of functions over or for the set var. Good. So what's the condition? We know what are variables. So what is the set cond of var? Is the set of Boolean conditions on the variables. So things like this, right? Maybe I can write down that x is larger than y, and maybe z equals 23, and s is something ak. Yeah. So we have a string variable, we have an integer, and maybe we have two integers that we compare, and the condition could be something like this. Yeah. So this is a Boolean expression over variables. So another example over here. Not x and y less than z plus 3 or w equals red. Suppose that x is a Boolean variable, so the domain is 0, 1. Y is an integer, so the domain is a natural number. The same holds for z. And w is a color. In this case, the color of a traffic light. And now what we define is we need to know for certain states whether we can take a transition. What does that mean? Remember my example? I had the loop condition that says while x is larger than 0, what am I going to check? I'm going to check whether this guard holds in the current state. And whether it holds in that state is defined mathematically by this relation over here. And this is defined as follows. So I do this by means of an example. So suppose that the current state tells you that x equals 0, y equals 3, and z equals 6. And now I would like to check whether this condition holds. Now, of course, not x holds because x equals 0. And of course, y is less than z because 3 is less than 6. That means that this state satisfies this formula. That's the way to read this. Second example, same state, different formula. X or y equals z. This is not true. Why is it not true? Well, x is 0, so this disjunct is false. Now we maybe have luck and we have to check the second disjunct, y equals z, but 3 is not equal to 6, and therefore this state does not satisfy this formula. Good. So what we now have is, we now have a mechanism. You give me a state, I look at the guard in my program graph, and I can decide, is the next assignment, while x larger than 0, subtract x from 1, is this assignment, can it now be executed or can it not be executed? Because for a given state, I can decide whether the guard, in my case x larger than 0, holds or whether it doesn't hold. The next thing I have to do, what is the effect of executing an assignment? This is relatively easy and formalized as follows. So we have a set of actions. Remember, actions are assignments that operate on the variables. Then what's the effect? The effect is described by a function that tells you, okay, give me the current values of all the variables. Give me the assignment I have to execute. Then the effect function is going to tell you what is the new value of all the variables. Mathematically speaking, this is a function. Remember, the values of all the variables is given by a function mapping variables to values. Yeah. This is an assignment. So this function effect takes an action, an assignment, plus a function and gives you back a function. Namely, a function assigning to all the variables in your program a value. Good. Example. I have 3 examples. The first example is the following. Suppose that I take an action and this action corresponds to this assignment. And suppose that the current state is something of the form x equals 1, y equals 3, and maybe there are some other variables, but they are not important here. Then the effect of alpha on this state is the following. Well, we have to execute this assignment. This execute assignment tells you takes 2 times the current value of x, which means 2 times 1 is 2, plus y is 3, so the next value of x will be 5. What happens to y? Well, nothing, right? Because this assignment doesn't change y, so that means that y isn't changed. It's not changed. Next example. Now we have the action which I call beta, is now the sequence of 2 assignments. The first is the assignment we had in the previous example, and the other one says y becomes 1 minus x. Now I want to describe what's the effect of doing those 2 assignments on the current state. Let's assume the current state is 1 and 3 for x and y. Good. What happens? X becomes 2x plus y. 2 times 1 plus 3 equals 5. Then we say y becomes 1 minus x. So based on this 5, we're going to say that y becomes 1 minus 5 is minus 4. And that's why we get minus 4 here. Yeah. This has to do with the semicolon here, that we take this assignment after we did the previous assignment. We model this in this case by 1 action, but that's why we here get minus 4, and not 1 minus 1 would be 0. This is different in the following thing, and here what I mean by this notation is a parallel assignment. So this is an assignment that takes x and y as a pair, and on the right hand side says x becomes 2x plus y and y becomes 1 minus x. Now this is different from this statement over here in the following sense. X is still to be 2x plus y, which means 2 times 1 plus 3 is 5. But y is now 1 minus x based on the value of x before this assignment, which was 1. And now we get 1 minus 1, and now we get 0. Yeah. So I'm going to use this syntax for parallel assignments, and this is sequential assignments. Good. But I hope the principle of this effect function has become clear. Okay. Any questions so far? Question?
The sequential assignment, this can be composed from individual assignments?
Yes. Yeah.
So I have the first effect application and the second effect application?
Yeah. Later what we're going to see is if you look at multi-threaded programs, you maybe would like to execute assignments atomically, which means in between those two assignments you don't want to have another thread doing a step while you are in the middle of doing those two assignments in a row. And there it makes sense to model this as one action. And that's where we're going to use this. Okay, any other questions? Doesn't seem to be the case. So let's now formalize what's a program graph and what's a transition system of a program graph. A program graph is a couple of locations, a couple of actions, the effect function, the function that tells you what's the effect on the variables if I take an action. This is the edge relation of the program graph, and remember those were the dashed edges in my picture. I have a set of initial locations and we have some initial condition on the variables g0. So formally, loc is a finite set of locations. So a transition system may have countably infinite number of states. A program graph is always having a finite set of locations. Why is this? Because a program is finite. Yeah? It has finitely number of lines, period. Good. We can also call them locations, and you can think about locations as control states. But I would like to separate the two things. Locations are the inputs of a program. States are the semantics of a program. They tell you what's the program location plus the values. These are two different concepts, right? Then there is a set of actions, assignments. Then there is this effect function. Given the current values and a certain assignment, it tells you what are the next, let's say the next values of your program. So this is a function that formalizes the effect of the actions. We have seen already an example. This is another example that tells you that x becomes x plus y. In this state, you add just 1 plus 7, you give you 8. And y, of course, is not changed. Then we have this edge relation. And maybe I should shortly remind you on this edge relation. Yeah, maybe you take the example as we had before. We had L1, we had L3. I think here was something like x is at most 0. Here we had an edge that says if x is larger than 0, then we do x becomes x minus 1. If I was not mistaken, you get to L2. And in L2 we had an edge that went here. And here we said that true, basically, and then we do y becomes y plus 1. And here we basically said something like loop exit. This was called alpha, this action was called beta. Yeah? So this was the initial location. So this relation over here is exactly the relation that goes from loc conditions over the variables and act to loc. So for instance, in my example, an element of this thing is L1, right? A condition, x larger than 0, an action, x becomes x minus 1, and another location, in my case, L2. Yeah? So this belongs to this relation, and that corresponds exactly to this edge over here. Yeah? The way to write this is, this is a bit awkward, so I'm going to use a similar notation as I introduced by the transition system. We say that L1 has an edge that goes to L2. It's labeled with if x equals larger than 0, then we say x becomes x minus 1. Good. So these are those kind of edges. We have a set of initial locations. In my case, I have only one initial location. And we have an initial condition on the variables. So maybe in my example over here, maybe we have initially, I don't know, that x equals 2 and y equals 0. And we call this condition G0. This is very precise. It uniquely defines what is the initial state or what is the possible value. Another example could be something like G0 prime, which says maybe x equals 20, and the only thing we know about y is that y is larger than 0, and maybe we also know that y is less than 10. Yeah, this could also be a condition. This specifies not a single initial state, but a whole set of initial states. Yeah? Or a set of initial locations, actually. Okay. Now what we have to do is we have to define a mapping that tells you for every program graph we get a transition system. Yeah? So how does that work? This defines as follows. So what I intend to say, every program graph, well, every behavior, the behavior of a program graph can be captured by a transition system. And I'm going to illustrate this as follows. I'm going to provide you a function that takes as input a program graph over a set of variables and gives you as output a transition system that corresponds to this program. Intention, the transition system is going to basically contain all possible behaviors of your program. So very similar as the hardware circuit before, the transition system models all possible behaviors of the hardware circuit. I now do the same, but do for program graphs. Now, what are the states? Now, I told you that the states actually contain two things, namely the program counter. Program counter means locations, those vertices over here, plus, the values of all the variables. What were the values of all the variables? Well, those were functions, right? So these are functions eta that map variables to values. Good. So states are pairs. Good. Then this is the input is a program graph. This is the formalization of such a program graph. And now I would like to describe the transition system of P. So for this specific program, what is its transition system? What is the representation of all its possible behaviors? Good, we just have seen states are pairs. So the state space is the Cartesian product of the set of locations plus all the valuations of the variables. Yeah. Here there may be many unreachable states. Yeah. I simply take all possible states. Yeah, it could be the case that here is a combination of the values of x and y, for instance, in my program, that I will never reach. But that's something that we are going to define by means of the transition relation. What are the initial states? The initial states, now where do we start? Well, definitely we start here, right? So we start in an initial location. So that's the first component. L is an initial location. Then, what I just said, maybe you have an initial condition that allows you to have many initial values. We have to consider then all possible initial values. And that's indicated by the second component. So I'm going to have a function eta, and the only thing I'm going to require that this eta must satisfy the initial condition. Yeah, so in my case over here, eta could be a function that says eta of x, I don't have much choice here, right? Because x needs to be 20. But for eta of y, I have several choices because the only thing I'm saying is it's strictly larger than 0 and strictly less than 10. So now pick your choice. So maybe you say 7. This is a possibility. Yeah? And this eta function, this eta satisfies g0 prime. Of course, I could make another pick. If you like 5 better, you take 5. It's still satisfying the condition, that's okay. If you make the wrong pick, let's say 10, 10 is violating this condition, so now I have an eta that violates this condition. And the only initial states I allow are those that satisfy the initial condition. Good. The hardest part is maybe the transition relation. So what's the transition relation? This is given as follows. So in the graph, we go from L to L prime. So let's make an example. In this graph, I move from L to L prime. I'm moving from L1, in my case, to L2. Let's suppose I take this edge. Okay? Good. So that means I'm going to take this edge. So in this thing, this is my guard. This x becomes x minus 1 is the action alpha, right? For the rest, what I know, I have to define the relation on states. So this is not enough. I only also have to fix what is the current value. So let's suppose the current value is as follows. Eta of x is, no, God knows what, 19. And eta of y is 7. Yeah, so I'm going to consider the current, now the state. Now, first of all, we have to check, does this satisfy the guard? Now this thing, this eta satisfies the guard x larger than 0. That means we have this edge over here, and we have an evaluation satisfying the current guard. So we fulfill the conditions that are written above the straight line. And then you should read this as follows. If this condition above the straight line holds, then the condition below the line holds as well. What does this condition tell you? Now I'm going to have a state in my transition system. So now I'm going to look at my transition system. So the transition system tells you, you are currently in a state L1. You currently have an evaluation eta. The evaluation that I told you there, that eta of x is 19, eta of y is 7. Good. So this is what I have here. Now what this rule tells you, you have an edge. So in the transition system, you can move from this state to that state by doing alpha. Okay, so let's do alpha. What is alpha in my case? So I can do here alpha. Alpha in my case is x becomes x minus 1. What is my next state? Well, my next state contains of L prime. What is L prime? Well, L prime is the value of the program counter after doing this. So I can read this off from my graph. So this L prime is actually exactly in my case L2, right? Because we take the orange edge in my graph. So what's the next valuation? This is eta prime. What is eta prime? Well, eta prime is the effect of what? Well, of doing the action, x becomes x minus 1, on what? Well, on this valuation, eta. Yeah. And this is what we already have seen. So what is this going to do? We know that eta is this state x equals 19 and y equals 7. And that means that eta prime is the following. The only thing that happens is that x is decremented by 1. So x is going to be 18. Y is not changed, so y is still 7. It's exactly what I think you expect. Yeah? It looks more complicated than it really is, but... Okay. So formally speaking, actually, this relation that we are going to define, that we just defined, is the smallest relation such that, and that's another way of writing it down in terms of the notation I have here, if the condition above the line holds, then I can conclude the condition below. So if this holds, the condition above the line, then I can conclude what is below the line. Smallest tells you only this. You cannot add new things. You cannot, let's say, imagine new transitions that for some reason. Yeah, it's really the smallest. Okay, so that's what we just have seen. Last part, what are the atomic conditions or propositions? Well, that's a bit, I would say, debatable. I mean, there are different ways to define this. In this slide, I said, okay, let's suppose that I can define what is the current location, and maybe we have conditions over the variables. So, and then you have a labeling function. So the labeling function takes a state of the transition system. Remember, these are pairs. In order to say in which location you are, you basically say this is the location we are, namely the first component. What do we know about the valuation? We basically can take any conditions such that the current valuation satisfies this condition. Good, and that's it. This defines for every program graph the underlying transition system. Mind, the transition system may have infinitely many states. How can we get infinitely many states? well, countably infinite many states, because we said I only use things like naturals, right, or integers, no floating points, no reals, right? So that means that I could potentially have a program that just counts, and this counter can be arbitrarily large, and therefore my program can have infinitely many states. And that's reflected in this transition system. Good. Now, how does this work for a typical language? So you can define something like a guarded command language, defined by Dijkstra, which is a typical kind of programming language that also contains non-deterministic choice. So the idea is the following. Every GCL program there's a one-to-one mapping to a program graph. And what we just have seen, every program graph can be mapped onto a transition system. So what this slide is basically saying, no matter which GCL program you give me, in the end I can reduce it or map it onto a transition system, which is an adequate representation of the possible behaviors of my program. So let's have a more detailed look at this guarded command language. So the way Dijkstra defined it was of the following form. We have a guard and then a statement. And this is only enabled if G is true. And then there are loops. Loops in Dijkstra's notation were of the form do. If this guard holds, execute the statement odd. So in my notation it would be something while G do statement. In Dijkstra's notation it's like this. So that's the way I would write it down probably. If then else. So this if G holds statement 1, if not G statement 2. So you can write this down like this. So this symbol stands actually for a non-deterministic choice. So in particular, what you can write down in Dijkstra's notation is something like this. Do. Then you say condition x is even. Then you can do a statement. You say x becomes 2 times x. Or you could say x larger than 0. And then you say x becomes x minus 1. Odd. This is perfectly well allowed in Dijkstra's notation. The two guards are overlapping. There are, of course, even numbers which are strictly positive. What is the program going to do if now x is, for instance, let's say the value 10? So suppose I execute this program in the state where x equals 10. The program non-deterministically is going to decide either to double x or increment x by 1. Yeah? Non-deterministically. Yeah? So this is typically something that is allowed in the guarded command language, but not in something like an ordinary programming language. So this is the syntax. You have assignments, you have sequential compositions, and then do and if. And the semantics of a program is basically a program graph. So here is a very simple beverage machine. And that's the last example of today. It's a machine that actually has only Sprite bottles and Coke bottles. It has a finite capacity. So there can be max number of Sprite bottles and max number of Coke bottles. So if max is 100, you can have both 100 Coke and 100 Sprite bottles and 200 in total. Then you can have actions. So maybe you flip in, you insert a coin in a machine and you can get a Coke. Well, this of course is only possible if there is at least 1 Coke bottle left. That means if the number of Coke bottles is positive, then you take a Coke bottle. The same for Sprite. When can you do a refill? So then in the cafeteria here, somebody comes, opens this machine and refills. My assumption is you refill up to the whole capacity. So this is always enabled. So this is just saying true. And now 2 things happen. I will both, let's say, put the maximal capacity on Sprite and Coke bottles. When can you insert a coin? That's always possible. Inserting a coin does not yet have an effect on the variables because you first have to indicate, do you want to get Coke or do you want to get Sprite? And then you can return your Coke or return a machine, so it's a fair machine. And that says, okay, if the machine is empty, you point in a coin, then you get back your coin, and this has not an effect on the variables. So a program that does this looks as follows. It is a loop which actually has two possibilities. The guard here is true, the guard there is true, which means this program is not going to terminate. It's a non-terminating program. You can always insert a coin, that's here. And if you insert a coin, then yeah, if there is no Coke and no Sprite, you get your coin back. If there is at least a Coke bottle, then actually you can get a Coke bottle. If there is at least a Sprite bottle, you can get a Sprite bottle. And the second possibility in this loop is that you refill, which is always possible, so that the guard is true. You refill, which means you refill both the number of Coke and the number of Sprite bottles. So this is user inserts a coin, no beverage available, select Coke, select Sprite, etc. I think this is clear. So this is the program again. This is a program graph that has two variables, the number of Sprite bottles and the number of Coke bottles. What's the graph? The graph looks as follows. There are basically two locations. So if I would draw the graph, it would look like something like this. There are two locations, so we have start and we have select. Then the initial location, what's the initial location? Well, the start is on the left bottom, so we start here. Good. What are the edges? I'm not talking about the states yet, I'm only talking about the program graph, right? What is possible in start? What are two possibilities? Let's first consider to the refill. What will be the refill? The refill will be, we have an edge, moves here. The guard says true. What can I do with the true? I can do a refill. We just have seen what is the effect of a refill. Effect of the refill is maximal capacity of Coke, maximal capacity of Sprite. So this refill is nothing else than an action like my alphas and betas before that actually tells you, right, that the number of Coke bottles becomes max, and the assignment, the number of Sprite bottles, becomes max. Then what else is possible? You can insert a coin. Okay, if you insert a coin, we go to the select edge, so you can insert a coin. When can you insert a coin? Always, so the guard is simply true, and then you can insert a coin. And now we are in select. Select corresponds to the if statement, the innermost if statement. What can you do with the innermost if statement? Well, if Sprite and the number of Coke bottles is zeros, we return the coin. And where do we move? We move to the start location because we will quit the if then else statement and we go to the outermost while loop. In terms of my program graph, it means I will have an edge going back here. And this edge is labeled by number of Sprite equals number of Coke equals 0. And what do? I do the action return coin. What are the other two possibilities? If the number of Coke bottles is positive, you can get a Coke. That goes back here. So if the number of Coke is positive, you get Coke. And here the same for Sprite. So here says the number of Sprites, you get Sprite. Yeah, so this is the program graph that one-to-one corresponds to this program. And this is the transition system. With one caveat, the transition system, I assume that the maximum capacity is 2. No? So if you assume that this max equals 2, then the definition, I gave you before, gives rise to this transition system. So first of all, you see, the states are of the form which location we are, so it tells you we are in this location. Initially, Coke are the fat circled things. If they are orange, it means they're filled, and otherwise they're gone. So here we start with 2 Coke bottles and 2 Sprite bottles. Of course, you can do a refill, but the refill will not change anything because the maximum capacity is 2, and it's already completely filled. You can insert a coin. Now you can either get a Coke bottle, which means 1 Coke bottle less, or you can get a Sprite bottle, which means 1 Sprite bottle less. You can then insert a coin again. Here you can still get a Coke or get a Sprite. If you get a Coke, then you see there are no Cokes left and there are only Sprite bottles. So if you then insert a coin, the only thing you can do is get a Sprite and not get a Coke, and so forth. Yeah? When can you do a refill? You can always do a refill. So for instance, in this state, you can do a refill, and that makes you go here. And this thing, start thing, you can do a refill and there. So anytime you are in this location, you can refill, which means in any state where the program counter is blue, I have a loop back. So also from this one, I can move and can move back, and so forth. This is for you not readable, neither for me, but this corresponds to the state where the whole thing is empty. Yeah, and from here there is also a refill, which is this arrow goes back here. Okay, this brings me to the end of this lecture. The next lecture is on Tuesday morning, 8:30. See you then.